Today we're going to see this application of the root locus method um, so that we can actually plot the root locus for different transfer functions. But before that, let's examine a little bit the concept of the root locus method and how we go about working in MATLAB to plot those. So let's look at this very simple um, control loop. And the idea here is that if you have the simple control loop where you have your system in here, G of S is your system, and you have a feedback in here, um, we could have the closed loop transfer function as you see on the right hand side. But the root locus method deals with a method that comes from Professor Evans at the University of Pennsylvania, who started this method back in the 1940s. And his idea was that if you change the value of k here from, let's say, 1 to infinity, every time that we change k, we obtain a new system, right? And then we obtain new poles and new zeros. Remember, the zeros are the roots of the denominator, and the poles are the roots of the denominator, and the zeros are the roots of the numerator of the transfer function. So in here, you see, if you have the representation, this would be a transfer function that you have where this is a, you have one 0 at 0, you have one pole at 0, and then you have a 0 at -1, and you have a, a pole at -2. How would the transfer function of this look like? This transfer function would look something like this. Let's see, transfer function. G of S, or whatever we want to call it. In here, we are seeing that the numerator of this is going to be S plus 1, and the denominator will look something like S times S plus 2, see? From here, if you set S plus 1 equals to 0, then it follows that S is -1, you see? This one corresponds with this. For the denominators, for the numerator, yeah? For the denominator, obviously S is equal to 0, and also S plus 2 is equal to 0. So from here we know that S is equal to -2. And this, say this corresponds to this, see? Yeah? So we could plot the location of these poles and the zeros depending on the value of that constant k, which we change from 1 to infinity. So if we have an application like this, for example, we would have a transfer function like I just gave you, similar to it, where you have the transfer function, which is the camera, and then the amplifier would be the gain. But you see, we could, if we have the transfer function, we could say when k is 0, the pole is -1, pole 2 is 0, k is 5 is -9, minus 0.53. So you see all the possibilities in there, and that is what we see in here. And you can see the root locus in here as we do different values of the gain. and we can put this into the MATLAB system. Okay, let me show you an example. These are different locations for the poles and the zeros for different transfer functions. Let me show you one that we can actually, I worked this out. So if you can enter this into MATLAB, like the first thing you do is define S as a transfer function type, and then you can enter G as S plus 3 plus S plus 4 divided by S plus 1 plus S plus 2. And then you do R locus, then you're going to get all the root locus that you have for the different values of the gain. So this is the real and imaginary axis, and with colors the program could tell you how they go. Okay, so that illustrates how we build the transfer function. I have a second example in here that you can look and try. This is the transfer function, and this is how you put this transfer function into MATLAB. And once you do root locus, then it'll give you all the locations of the roots as a function of the gain. Obviously, at this point, you could see there's a transition between the stable and unstable system. But this is how we obtain the transfer functions for this particular transfer function. How we obtain the root locus.